elementary review of the Laplace transform today. The Laplace transform is a way of taking a function f, little f of t, and changing it to a different function, capital F of s. And as we change s and look at how capital F behaves, we can say things about little f of t. The function is formally defined like this as an integral from 0 to infinity of e to the power minus st times little f of t dt. And this integral needs to converge for all s which are sufficiently far in the right half plane, with the real part of s and the imaginary part of s. If it is sufficiently far in the right half plane, then it needs to converge. It doesn't matter if it converges to the right of this line or to the right of this line or to the right of this line, but there has to be some line to the right of which this integral converges. So for example, functions little f of t that grow like polynomials multiplied by exponentials, such functions are allowed, because if I take s to be more to the right than k, suppose k is 10, if I say s is to the right of the line cutting through 11, then it is fine, it will converge. But for example, e to the power t squared is not included. The inverse Laplace transform is formally defined through this integral, the Bromwich integral, which is on some vertical line to the right of all singularities of capital F. But in practice, we will invert it by inspection and small tricks, as you will see. Here are some examples. The Dirac delta function at t is equal to 0. If we want to find the Laplace transform of this, then we can't have the limit exactly at 0. So we take the integration domain as 0 minus, just a little bit to the left of 0. I'll remind you that the Dirac delta function can be thought of as this impulse at 0. It is this infinitely thin, infinitely tall spike at 0. The Laplace transform of delta of t is then just this integral. The limit is from 0 minus to infinity. This Dirac delta function pulls out the value of this thing here at t is equal to 0, which is 1. So it is independent of s. The Laplace transform of the function 1 of t. So over here to the left, for negative values of t, we think of it as 0. It never enters our calculation here. We only look for positive t. 1 of t rises from 0 to 1 and then stays constant. This is also called the unit step function. When we take its Laplace transform, then this is easily integrable. We get e to the minus st by minus s. For t going to infinity and s positive, or with a positive real part, what happens is the exponential goes to 0, and so this becomes 1 over s. And you can see that this integral converges for s in the right half plane. Suppose we have e to the at. Think of a as a real number for the moment. Then 0 to infinity e to the power minus s minus at is the Laplace transform of this function. And we find by similar arguments that it is 1 over s minus a, only now the real part of s has to be greater than a. So it has to be to the right of some value. This distance would be a. If a was negative, then it would just have to be to the right of that particular location. It doesn't matter. In both these cases, you can see that the integral converges when for all values of s sufficiently far in the right half plane. So in the previous panel, I said think of a as real, but now I'm going to use a small trick. Think of the Laplace transform of e to the I omega t, where omega is real. This is actually the Laplace transform of cos omega t plus I sin omega t, as you know. But because of this form, it is also 1 over s minus I omega, and it can be written as s plus I omega by s squared plus omega squared. And formally separating real and imaginary parts, tentatively thinking of s as real, which is why I am saying it's a trick, you can remember, therefore, that the Laplace transform of cos omega t is simply going to be s by s squared plus omega squared, and the Laplace transform of sin omega t is going to be omega by s squared plus omega squared, as I have written here. Suppose we have the Laplace transform e to the at times little f of t, where we've already gone through the work of finding the Laplace transform of little f of t. Then we see that in this new transform, basically s becomes replaced by s minus a, and so the Laplace transform of this function here is the old Laplace transform only with s replaced with s minus a. Given that capital F is the Laplace transform of little f, here's another small trick. If we take the negative of the derivative of f with respect to s, we can take the derivative inside the integral sign. And when we take the derivative of this thing with respect to s, we just get a minus t. Because of the minus sign, the minus goes away and the t remains here. So the net result is that the Laplace transform of t times little f of t is the derivative of the Laplace transform of little f of t and then multiplied by the minus sign. Suppose we want the Laplace transform of f dot or df dt, we write it out here, then we do integration by parts. We take this to be the first function, this one comes out, this one gets integrated, and then when we differentiate this, we get a minus s, but then the minus sign becomes a plus, the s is here, e to the minus st, and this f of t has come here. So you can see that this one here, integration by parts is this here, and now over here what happens is as t goes to infinity, this e to the minus st squashes the little f of t, and so the upper limit is 0, and the lower limit gives us a minus f of 0. That's this minus f of 0. And this part I can pull the s out because it is not part of the integration, it's constant. T is the variable of integration. And so after I pull it out, I see what I have is capital F of s. And so the Laplace transform of f dot is little s times the Laplace transform of f minus f of 0. Similarly, I have a mistake here. The Laplace transform of f double dot is then s times the Laplace transform of f dot minus f dot at 0, which works out to be this, and so on. We can go as many derivatives as we want. The Laplace transform of f of alpha t for alpha greater than 0, alpha is a scaling thing. So suppose we change units of time or we scale time in some way, then what happens is we have the integral from 0 to infinity e to the minus st, then f of alpha t dt. But this alpha t suggests to us that we should turn this t into alpha t and this t into alpha t. Turning this t into alpha t over here makes us put this s by alpha here. Turning this dt into alpha dt requires us to put a 1 over alpha outside. And after we do this, we realize that alpha t can just be the new variable of integration. This is d of alpha t. And so s gets replaced by s by alpha, and there is a 1 by alpha outside. And so the Laplace transform of little f of alpha t is 1 by alpha times capital F of s by alpha. If g of t is the integral of little f from 0 to t, this is a definite integral. Suppose you don't want to use a definite integral, then you can add a constant to it, and that's the indefinite integral. But we'll just do the definite integral because the constant is the Laplace transform of the constant is just constant times Laplace transform of 1, which we know already. So we won't worry about the constant. Let's worry about this. The Laplace transform of g of t, we write it like this. This here is g of t. And then what we do is we take this as the function to be integrated, this as the function that comes out through integration by parts. So g of t comes out. The integral of e to the minus st is e to the minus st by minus s. And then we have a negative times the integral of the derivative of this one times that. This one has the negative in here, so that negative becomes a positive. This s from the denominator stays outside because it doesn't participate in the integral. The e to the minus t just goes here, and the derivative of gt is g dot of t, but if you look at the definition of g, you will see that g dot of t is just little f of t. And so this becomes little f of t, so this integral becomes capital F of s, so it is capital F of s by s. This one goes to 0, provided there is some s sufficiently far in the right half plane so that it squashes g of t. And if f is growing at most as fast as exponentials, then the integral of f is growing at most as fast as exponentials. It can always be squashed. So there is for s sufficiently far in the right half plane, this first part is going to be 0. I mean, the upper limit will be 0 and the lower limit is 0 because the integral is 0. So it's going to be 0, and this is going to be capital F of s by s. Okay. From the last panel, we are looking at s times f of s, where capital F of s is the Laplace transform of little f of t. In the limit as s goes to 0, this works out to be the limit of f of t as t goes to infinity, provided that exists. And as s goes to infinity, this works out to f of 0, provided that exists. And the reason this works is that s times f of s minus little f of 0 is the Laplace transform of f dot. I've moved the f of 0 over to the right-hand side. And now if I take little s going to 0, this is 1 essentially. This integral becomes f. So I get f at infinity minus f at 0 plus f at 0. So that's f at infinity. So that's the limit as s goes to 0. And as s goes to infinity, what happens is this integral really squashes smaller, smaller, smaller. So this integral goes to 0 and I'm left with f of 0. Those are the two limits. The convolution of two functions f and g is defined as this integral from 0 to t, and then f evaluated at t minus tau and g evaluated at tau integrated with respect to tau. These two can be exchanged. So I can have f of tau and g of t minus tau, and I'll get the same result. These two are the same. The reason why I'll get the same result is you can set u is equal to t minus tau as a new variable and work through the calculus. You'll see that you get it. So the Laplace transform of the convolution is the integral from 0 to infinity with respect to t multiplied by e to the minus t, and here is the function itself. The convolution is this thing inside the square brackets. Now e to the minus st does not depend on tau, so it can be moved into the integral, and once I do that, it becomes a standard double integral. When I look at this double integral, I see that I'm doing the tau integral first from 0 to t. Here is the t tau plane. What happens is that t is always bigger than tau, and so I am above this 45-degree line. Tau begins somewhere at 0 and goes to t. So I get a horizontal strip. I cover many strips like this, and in this way I cover the triangular region above this 45-degree line. I can change coordinates and I can do the I can change the order of integration and I can do the t integral first. When I do that, I come here, I have the t integral first. You will see that the limit for t goes from tau to infinity. So here is the t integral being done first, tau to infinity, and then tau goes from 0 to infinity. Now if I make a small change of variables, t minus tau is equal to u, I do this only for the t integral part where tau is a constant. I find that dt is du. Once I work through the details, I find f of tau remains the same, g of t minus tau becomes g of u, t becomes u plus tau over here, du d tau. But then I can separate things out. I find it is the product of two integrals, one with respect to tau, one with respect to u, and it is the convolution of this leading to the product of capital F and capital G. You need to examine tables of Laplace transforms in books and practice inverting simple ones by hand. For example, invert this one, that's a quadratic, easy to do. This one s cube, and here is a fourth order polynomial. So over here I would be happy if you found the roots using a calculator, expanded it in partial fractions, and then found the inverse Laplace transform. While there are complications and special cases, a simple trick for partial fraction expansion is when the denominator has distinct roots. So for example, some polynomial here, and then s plus a times s plus b times s plus c times s plus d, all distinct. These could be complex, I wouldn't care. Then this can be expanded as capital A over s plus a, capital B over s plus b, and so on. And then I still need to find these constants. And the way to find it is to multiply both left side and right side by s plus a, for example, and then taking the limit as s goes to minus a. So the s plus a here, they go to 0, and I just get capital A. And over here, when I multiply by s plus a, I cancel this term, and then as I take the limit as s goes to minus a, basically I put minus a here, here, and so this capital A is this quantity here. You can find it directly, but I'm sure you know other ways for more complicated cases, especially including repeated roots. The first application of Laplace transform is in the solution of ordinary differential equations here. So we have this second order differential equation, x double dot plus 4x dot equals cos omega t and some initial conditions given. We take Laplace transforms of x double dot is s squared times the Laplace transform of x minus s times the initial value of x minus the initial value of x dot plus 4 times this Laplace transform, which is s times the Laplace transform of x minus x dot plus 7 times the Laplace transform of x. I hope you are paying enough attention, and I hope it is clear that this is little x, this is capital X, that's the function of t, this is the Laplace transform. And then on the right hand side is the Laplace transform of the cosine. I collect the coefficient of capital X, so one from here, and one from here. I move everything else to the right hand side, I divide by this, and I get capital X, which I will invert. The right hand side works out to be some polynomial divided by this second order quadratic polynomial and this s squared plus omega squared. When I expand this in partial fractions, you can see that from here I'll get a sine omega t and a cos omega t, and from here I'll get decaying exponentials. So that's the inverse Laplace transform. I haven't worked it out. You can if you wish. If we have a system of equations, x dot is equal to ax plus bu, where a is this A, capital A, is now an n by n matrix, x is an n by 1 column matrix. Think of u as a scalar input, single input, b is an n by 1 column matrix, and the initial condition vector x 0 is n by 1. And we have an output which is y is equal to cx, cx is a row matrix. This is not just a mathematical abstraction, this is the linearized constant coefficient version of the standard dynamic system that we are going to consider in control. So for example, there are many possibilities, but let me just give you an example. Suppose there is a cantilever beam that is vibrating, and maybe 6 modes are retained in your model. You write your equation, you will get n will be 12 because you'll write it in first order form. Let's say you have a strain gauge at some place, and what that strain gauge is going to do is pick up the modal displacements of all 6 and give you a linear combination of them, okay, assuming that only 6 modes participate. So in this way, what you will get, this C will have influence coefficients for each of those modes, some coefficient, and in this way you will get an output. When I take a Laplace transform of x dot, I get s times the Laplace transform of x, and then I get a minus initial condition, which I have now moved over to the right hand side. This ax I have moved to the left. That capital X is the Laplace transform of this little x. This b is the same as this one. This capital U is the Laplace transform of that u. I solve for x. So I have si minus a inverted, multiplying the right hand side. That gives me capital X. My output y is c times x. So I have written a c transpose here. I shouldn't write the transpose. So this C is a row matrix. So I shouldn't put this either. Okay. So so now y is C, then this matrix here, which is some complicated function of S, times B times U, and then C, again the same matrix here, times x naught. The output is therefore composed of 2 parts. This second part here is a consequence only of non-zero initial conditions in the absence of forcing, and the first part is a consequence of forcing in the absence of initial conditions. The solution to linear systems can be split like this. When we are doing control systems, we frequently ignore initial conditions because assuming that the system has been stabilized, that's why we are studying it. Initial conditions contribute to some transients that die, and then we are interested in how the system behaves. But more importantly, over here you will see that if initial conditions are 0, over here you will see it is a product of one Laplace transform, which is of the input, times another Laplace transform which is a property of the system. This is a row, that is a column, this is a matrix. So this is a scalar quantity. It is a Laplace transform of some function. That function is what the output is when the system is given a unit impulse at time t equals 0 while starting from zero initial condition. Zero initial condition means this is gone. If u is a Dirac delta function, then its Laplace transform is 1. And so you see this is the impulse response function of the system. And in fact, the solution is a convolution of the impulse response function with the input plus something that depends on initial conditions. This is the transient solution. You may be familiar with linear constant coefficient differential equations. You know that the solution has exponentials in it. The solution for this has exponentials in it, and those exponential rates are the eigenvalues of A. And you may wonder where that occurs over here. And that occurs in this matrix. This matrix, which is the inverse of Si minus A, is actually the cofactor of this matrix divided by the determinant of the matrix. The cofactor has polynomials of order up to n minus 1. The determinant is an nth order polynomial. And so this, when multiplied by C and B, gives you some transfer function which has polynomials of order n minus 1, a polynomial of order n minus 1 in the numerator divided by the determinant of Si minus A. And Si minus A is really just the characteristic polynomial of A. The roots of Si minus A are in fact the eigenvalues of A. So when you expand it in partial fractions, eventually you will get exactly exponentials with exactly the rates being equal to the eigenvalues of A. Finally, if the eigenvalues of A all are in the left half plane, then those exponentials will decay and the system will be stable. If there are any that are exactly on the imaginary axis, these terms over here can lead to sines and cosines that are oscillating indefinitely. Same here. And if there are any eigenvalues of A in the right half plane, then there will be exponentially growing solutions. So based on the solutions from the previous panel, imagine that there is some system G of S. That's the transfer function now. Given an input u, the output is G of S times u of S. That means that the initial conditions in the previous solution are taken as 0. This is actually a convolution integral, but you will see rapidly that looking at it as a product has very big advantages. So for example, if the output of G is an input to H, then what happens is u goes in here, comes out as u times G, that goes in here and comes out as G times H times u or H times G times u. So first of all you have this multiplication, but secondly you have this mathematical equivalence between GH and HG. Physically you may not have that equivalence, and therefore you may not realize the advantages of whatever mathematical insights you may get from this equivalence. Here are two different plants, two different transfer functions, but you arrange them in a sequence and it just gets multiplied, so it is easier. But if you did convolutions on convolutions, you would lose insight very rapidly. More than that, you can do feedback, which is something that you do in control. So, for example, if here is an input and here you have something that does subtraction. So whatever comes back will be subtracted from you and then fed here. This will go through maybe a gain, like a gain on amplifier volume knob, some constant K, then through some compensator whose transfer function is C1, then fed to the plant whose output will be Y. This Y will be fed back through another compensator or little card or some transformation device or whatever it is, whose transfer function is C2, and then YC2 will be fed back here. So what happens is U minus C2Y is what this is. That multiplied by KC1G is Y. And we can do algebra like this with loops of this nature. And when we do that and we write it out, what we get is U KC1G right there is equal to Y times 1 plus Y times KC1 C2G. So 1 plus KC1 C2G times Y, which means Y is equal to KC1G by 1 plus KC1 C2G times U. this thing inside the dashed circle. This is the closed loop transfer function. So this is what feedback has achieved. If I have this gain knob, it will appear on both sides. If I don't have a C1, then that is 1. This will go away. If my feedback is unity feedback, that means there is no transformation of the feedback, this C2 will not be there. I can take just the plant, just the gain K, feed it back, and then I will get Kg by 1 plus Kg. When I look at the system transfer function G, points S where G of S is 0, these are called the zeros of G, they affect the dynamics. Points where G of S is infinity, these are called the poles of G, and they affect the dynamics even more. G, as we have seen, is in the previous example, it was some polynomial divided by some other polynomial. The poles of G are the places where the denominator polynomial is 0. Right? So, if there are poles of G in the right half plane, then just this system here would be unstable. It would give us unbounded inputs. But in the presence of feedback, that may no longer be the case. So, for example, when I use Kg by 1 plus Kg, it may happen that the poles of this closed loop transfer function are all in the left half plane. Let me emphasize that where I have this C1G, I will not put zeros in C1 in the right half plane to cancel the poles of G. That is a bad idea, because you will, in practice, you will not get exact cancellation and the poles will survive. So, we will not use zeros of C1 or C2 to cancel the poles of G, but the poles will shift anyway. For example, when you look at this, the places where G is infinite, at those places Kg by 1 plus Kg is 1. So, those are no longer poles. The poles are now at points where 1 plus Kg is equal to 0. If you think of 1 plus Kg being 0, then you see if K is extremely small, then for 1 plus Kg to be 0, G has to be extremely large. So, when K is very small, in that case, in such cases, the poles have shifted only slightly from their old values. But for larger values of K, it may happen that all the poles are in the left half plane, even if originally for G, some of the poles were in the right half plane. We will study this more as we study control theory.